Could power New York City, and you wouldn't need wires or anything like that. All right, so I've got my light bulb tied to the end of this thing. I'm going to turn off my screen here just for a minute. I'm going to turn off the lights in the room. Okay, so it's getting dark in here now. All right. So let's see. All right, so it's much darker in here. I've turned off the lights. We want to see if this thing will start glowing when I make my device. Okay, so the other critical component of my device here is I've got this thing. So I'm going to create a spark gap here. All right, I'm going to turn this on. Okay, so we've got this thing going now. Now I'm going to come in here with my light bulb. We're going to see if we can get. I don't know if you can see it or not. So if you see it, my light is turning on a little bit. Okay, so I'm actually lighting up my light bulb. If I get the right frequency, I can keep it on, but the light is flashing, okay? So I'm transmitting power wirelessly to my light bulb here, okay? So getting some good flashes there. So the bigger I have my gap, the stronger it lights up, okay? And I'm gonna get it really close. There we go. It's blinking, yay! Okay, so I'm gonna turn this off now. All right. So that's pretty cool because what we showed here is that we can transmit power to our light bulb. We can get it to turn on, and we did it with our little apparatus here, okay? Because we charged this thing up, okay, and then we quickly discharged it through our through the metal sphere here. So the current, so this thing quickly changed. So we had a rapid change in the electric charge, which also means there was a rapid change in the electric field. Now, because this is charging up and rapidly discharging, since we have a lot of charge moving around, well, then that probably means there's a changing magnetic field. So the next experiment is, let's see if there's a magnetic field. Let's hook up my compass here, and we'll put this in our light bulb here, okay? And I don't want to actually hold the compass because it's metal and it's probably going to shock me. So we're going to look for deflections in the compass, and maybe you can see my compass, or okay, well, there's the compass needle. Okay, so we'll turn this thing on again. It's a little scary, but it's also cool. So there we go. Get my hand away from there, and let's put our well, I don't really see anything in my compass happening. Nothing really to speak of happening in my compass. So, well, probably if there is, let's say, a magnetic field, it would be changing really quickly. So my compass wouldn't be able to pick it up. So if I were going to do this, I would need to get a Hall probe and hook it up like that. Okay, so All right, so that was a pretty cool experiment. We had the Van de Graaff generator here. We lit up a light bulb. I don't know if we can measure a magnetic field, but I think that there should be a magnetic field. Okay, so this is sort of like a Tesla coil. We were able to transmit power to our light bulb. Now, so if you did this and you went under a high voltage line, this thing should lift up, or this thing should light up. It should turn on if you get close enough. But this part will have a voltage, so don't touch this part because it could shock you. So basically, what I'm telling you is that you could have a short between here and this part, and it could shock you. So moral of this story is don't play around power lines. Okay. All right. So let's do another experiment, and then we are going to yeah, don't don't fly kites around power lines, and don't hold the light bulb up there. It will turn on. I think it will. Maybe I'll find a way to well, this is basically the same principle. Okay, so let's do another experiment. I'm going to switch cameras, so just for a second. Just a second. We're going to go over here, and we are going to look at we're going to make what's called a cyclotron. Okay, so today is fun because we're making two different devices. Yay, that's always fun. Okay. So here I've got this is my cathode ray tube. You can see it right here. Let me turn it on. Okay, so my cathode ray is going to heat up. There's going to be a little glow that starts to appear up in here somewhere. Sounds like a transformer. Oh, cathode ray. Yeah, that sounds like a pretty cool transformer. Okay, so much cooler than Megatron or Starscream. Yeah, Cyclotron, the Transformer. Oh yeah, he's definitely a Decepticon. Okay, so the little filament is starting to glow. I'm going to turn on the voltage, and there goes my beam of electrons. Okay, so I've created a beam of electrons. It looks like there's actually two beams, and they're a little bit curved, probably because of my magnets over here. So I have these really strong magnets, and you see the beam moving a little bit. It's because I'm holding my magnets about 2 feet away and then moving them around. All right. So here's my cathode ray tube. Now I've got let's see. I'm over here. You can't really see it. It's too dark. Exposure. Turn up the exposure. There we go. Oh, there we go. Okay, so here I've got a solenoid. I'm going to put my solenoid right next to my cathode ray tube here. And we've been talking a lot about what happens if you have a bunch of charged particles in a magnetic field. Okay, and we did this before, but now we're going to create a miniature cyclotron, and this is in 28.5. And what it does is when you have a charged particle and it flies into a region of magnetic field, it will go in a circle. And if you have a cyclotron, you can use this to accelerate charged particles. Okay, and you might want to do this for cancer treatment. So if you can take protons and accelerate them, you can shoot them at a tumor inside of the human body, and you can actually treat a tumor like that. Okay, so let me turn on my magnetic field. Oh, there we go. So when I turn on my magnetic field, you can see that it creates a curvature in my electron beam. Okay, so I'm going to turn up the kinetic energy of my electrons. Oh, that's a little bit bright. Let me turn down the exposure on my camera. Okay, so there's my beam of electrons, and I'm applying a magnetic field now. I'm going to turn up my magnetic field. I'm going to get this at the right angle. If we do it just right, then I can create a little, so right inside of here, Alrighty, so let's see. There we go. Oh, there we go. Some nice little spirals right there. There we go. So when I turn up my magnetic field way too high, I can get a little loop there. Okay, so now this is a little bit different because the magnetic field is not exactly perpendicular to my beam of electrons. Okay, but if it were, what would happen is the electrons would go in a circular orbit. So if I turn up my energy of my electrons, okay, then I can get a nice little loop here. And so in a way, I'm creating a cyclotron. Okay, so I'm making a little cyclotron here, and you can see the nice little spiral shape here. If I look down the beam of electrons, and I've created a little circle of electrons. Okay, so I'm making electrons go into a circle. All right, so this is like a little cyclotron here, which is pretty cool. Now, let's talk about cyclotrons. And I'm going to turn my lights back on so I can draw something. Just 1 second. Let me turn the lights and go back to my notepad. Alrighty. Okay. Here we go. All right. So, what is a cyclotron? Let's look at a little schematic diagram of what a cyclotron is. So a cyclotron looks something like this. Now, imagine that if you use this for a cancer treatment, okay, in the middle here, the source would be a piece of plutonium or something that is giving off radioactive particles. Usually in cyclotrons, they use something that will generate protons. So and in the cyclotron, so in the cyclotron, then it would accelerate the protons, and it would make them go in a loop. So if we look at our picture here, our protons would fly out of the beam, and they would go into our patient. So our patient here is this green blob. Okay. Then the protons would fly out here, and they would go into the tumor and the prostate, and then you could get another magnetic field and slow them down through collisions with the tumor walls, or with cells in the tumor. But what you need to do is you need to use your cyclotron to accelerate those charged particles. Okay, so so in here, here's our source, okay? In the middle, it's drawn into these two blue regions. So if you look at the screen, there are two halves of a circle, and each half would be a hollow metal hemisphere. Okay, so the protons would be free to fly around inside, and there's a gap between the two plates. And you're also applying a very, very strong magnetic field. Okay, so the magnetic field is represented by the green dots, and it's coming out of the page. All right, so the magnetic field is coming out of the page. You got this charged particle moving around in there, and they put this gap in there because they apply an oscillating electric field, so a potential difference between the two halves of the plate. So as the particle is flying around and it goes through the gap, then they put one plate at a very high potential. And so in the region in between the plates, so right in here, your charged particle is accelerated, okay? Because you've got an electrostatic potential between the two plates, and they change the potential really fast between the plates, okay? but only in that little region between these two metal plates is their acceleration. Because remember, because of Gauss's law, you cannot have an electric field inside of the metal plates. Right? So in those conductors, there's no electric field, and so you can't accelerate the particles. Right? Because remember, with a magnetic field, right, you can't change the linear or the linear velocity of the particles. You can't linearly accelerate it. You can change its direction, but you can't increase the speed using a magnetic field. Right? So you can change its velocity by making the charged particles path different, okay? But you cannot increase its kinetic energy. So what am I talking about? Okay, so let's go here. So if my particle is going this way, okay, and I draw my velocity vector right there, which is tangent to the path, okay? Well, what the magnetic force does is it changes its direction, okay? So right here, there is a change in the velocity. Not the magnitude of the velocity, but the direction. Because the magnetic force is acting perpendicularly to the motion of the electron. It's changing the direction of the velocity, but it's not increasing its speed. So if it was moving at, say, 15 meters per second before, if that was the charged particle's speed, then it's still moving at 15 meters per second, just in a different direction. Okay. So with our proton treatment here, okay, if we want to, cure the tumor in our patient, okay, so our patient's over here, he's this green dot, then we need to give the protons as much energy as possible, because when they get inside of our patient here, so we have another magnetic field. Oh no, that wasn't. No, what am I doing? Oh, there we go. Okay, I didn't have the draw function on. There we go. Okay. So we want when the protons get in the patient, we have another magnetic field that makes them go in a spiral over here. And when protons are inside of the human body, they undergo collisions with all sorts of things inside of your body. And so if you have that magnetic field there and you start making them go in a loop inside of the tumor, they'll start colliding with all of the cells in the tumor. And once a proton has a collision with a tumor cell, its kinetic energy gets converted into thermal energy. And so then you can, in effect, cook the tumor from the inside out. And so basically when the protons, are, I can't see my mouse right now. So the protons fly in here, they don't really interact with the human body that much until you get into the tumor, and then they start going in a circle. And there's a very low chance of collision, but you keep them there long enough, they will have enough collisions with cancer cells. And this treatment is great because you really just focus the radiation right there in the tumor, and you're not going to irradiate anything else around the tumor, which that is the problem with chemotherapy. So if a person is doing radiation treatment, right, the problem is that you're not just killing the tumor, right, but the radiation is cooks everything, right? So it kills all the healthy cells, right? So let's go back to green here. So let's say you're doing X-rays. What they usually do is they have an X-ray gun. So here's our X-ray gun. Let's say this is our X-ray gun here, and let's make a solid one. Okay, so here's my X-ray gun, and my X-rays are coming out of here. And if you're using X-rays, then the X-rays would be right here. Okay, so X-rays fly through the body, they hit the tumor, but they're also hitting all of the healthy tissue too. And so what doctors will do is they will start moving the radiation source around the patient. Okay, so every time they go to a different angle, now you're shining radiation from a different angle into the patient's body. Right? So, and every time you move your radiation source, then the radiation you see is being focused in this middle region in the tumor right here. Okay, so that's the highest area of radiation, is right where the tumor is. And so by doing that, then the healthy tissue gets a very minimum amount of radiation around the tumor. And most of the radiation is focused right there in the tumor. And so if you can do that, you can minimize the damage to the healthy tissue around the tumor, and you can really just focus on delivering the maximum amount of energy directly on the tumor without trying to damage too much of the healthy tissue. So that's one strategy for chemotherapy they use, which is different than a cyclotron. With a cyclotron, it's much better because you're really, really focusing it there right on the tumor. Okay, so if you are a doctor, and all right, I'm gonna erase all this stuff. So if you're a doctor, you might want to use proton treatment to treat one of your patients with prostate cancer. And so in order to do that, we need to know what the frequency is of the cyclotron. Okay, what is it's called its resonance frequency. Okay, what's its resonance frequency? Because that's the frequency you need to apply that electric field to your cyclotron in order to accelerate the electrons. Okay, and that frequency, it's a frequency of oscillation. And so let's talk about how you would find that particular frequency. Okay, well, all right, I'm going to stop sharing my screen with you. All right, so let's talk about the equation. How do we calculate the resonance frequency of our cyclotron so that we can do this amazing cancer treatment for patients? All right, get out of this. All right, well, we're going to, of course, start with our favorite equation for magnetic force, which I hope you all know by now because I don't know how many times I've written it, but it's a lot. All right, so we know that the magnetic force is, of course, equal to Q times V cross B. Okay, now in the cyclotron, okay, we have our velocity of the electrons or protons, let's say protons. And if our magnetic field is coming out of the page, which I'm representing by these little dots, or sometimes you might see it with a circle with a dot in the middle. Okay, that's like, imagine an arrow pointing out of the page. Or sometimes you'll see a circle with an X through it. If it's a circle with an X through it, that means an arrow pointing into the page. You can just draw it with little dots here. So we'll say these little dots represent the magnetic field pointing directly off of my piece of paper. So if my charged particle comes in here with some velocity v, then let's use our right-hand rule. And let's say this is a positively charged, this is a proton. Okay, so in our proton treatment for our patients, then we need to know, we need to have the right polarity of magnetic field so this thing actually goes in a circle. Okay, so let's use the right-hand rule. We will put our fingers in the direction of the magnetic field. Okay, well, can't, funny angle. And then, no, in our velocity, then we curl around up. So let me, okay, so here our finger comes in this way. Then we curl up. So we start in the direction of our velocity. We curl up, and then our thumb will be pointing downward here. Okay, so that means our force is pointing down. B is coming out of the page. So our electron is going to go in a circular path, something like this. Okay, that's the path of our electron. And so inside of our cyclotron, this is going to be the direction of rotation. And we need to figure out what is the frequency, right? In order to do that, we need to know what the radius of this circle is going to be. And this is supposed to be a circle. I didn't draw it. Okay. That's the radius of our circle. Hey, well, we did this last time. We know how to find the radius of our circle because we can set, all right, we'll say the magnetic, the force, the magnetic force on the charged particle is equal to our centripetal acceleration, okay? V and B are perpendicular, so sine of 90 is equal to 1. So this will give us Q equals V times B, which is also equal to M V squared over R, okay? So this is what we did last time, and this will definitely be on the test. R is right here, so you did this problem last time. It's gonna be on the test, I'm just telling you now. The test is on the 16th. It starts on the 16th, so all right. So now we need to get an expression for frequency. How do we do that? Well, I'm going to tell you, because we didn't do the chapter on angular motion, and so I'm going to, in physics 1, I'm going to explain it to you now. That was one of the things we skipped, but we're going to come back to it right now. So first what I'm going to do is I'm going to cancel out my V's here, and I will get V over R equals Q times B divided by M. All right, great. Well, all right, so now we're at a place where we need to talk about what angular frequency is, okay? So angular frequency is, if we said F is my frequency, that would mean that if my charged particle goes in a circle 2 times a second, then my frequency would be 2 hertz. Okay, so frequency is, frequency. Okay, so this is my frequency. And if it goes in a circle 2 times per second, my frequency is 100 hertz. If it goes 100 times, then that's going to be 100 hertz. Okay, this is frequency. If we want to find our angular frequency, which is a quantity which is omega times 2 pi f, okay, this is our angular frequency. All right, so all right, another way we can get this is we angular frequency is defined by the its velocity times a particle's radius. So if you're going in a circle, you take its linear velocity, right, and you would divide that by the radius, and that will give you frequency. Okay. Now, what are the units of frequency? Let's look at our expression right here. Okay, so let's say v, our velocity, so this is omega times v over r. Well, our velocity, so velocity is dx divided by dt. So that is our linear distance divided by time times 1 over r. Okay, so this is our radius here. Okay, right? Well, what is the circumference of our circle? Okay, circumference of a circle. So C equals 2 pi r. This is the distance around our circle, 2 pi r. Okay, and if we divide this by time, if we divide our circumference by time, this will be dt divided by dt here. Okay, now this will give us our the number of rotations per second. So this is basically our velocity, okay? Because we have a distance here, our circumference, which is a linear distance. We divide that by time, and this will give us a velocity, okay? So now we have, but it's a, so now we can write 2 pi r divided by t, right? Well, we go back up here, right? So let's go back up to frequency. We're going to say omega equals 2 pi f. And we said that this is equal to v divided by r, right? Well, if we say f, okay, we divide this, so we have v divided by 2 pi r here. This is the circumference of our circle. So our frequency is equal to v divided by c. All right, this is an important result for angular motion because now we're saying that our linear velocity divided by the distance that it travels is going to give us our frequency. What are the units of frequency from my little mini derivation here? What are the units? You can put it in the chat. What are the units of frequency? So let's see if anyone is still watching. Are you actually watching physics? I see there are 27 people. Put your answers in the chats. What are the units of frequency? They are hertz. That's true. Yes. So it's hertz, but what are hertz equivalent to? You're right about that. It is hertz, but what's hertz equal to? Yes. Hertz is 1/second. So yes, people are paying attention. Thank goodness. All right. So from our little definition here, so v divided by c, this is our velocity here, divided by the distance is equal to frequency, which is 1/second. Okay. So let's if we have, let's go back to our first semester and we'll say, what is, if you recall this equation, x equals v times t. Do you guys remember this? Okay. So in this expression here, let's say c is our circumference. Okay, so c is our circumference. That's the distance around our circle. So we'll say that x equals c. Okay, now we can write this as c times v times t. Okay, well, what are we doing here? Sometimes I ask myself that question too. What am I doing in life, Dr. Wisby? I don't know sometimes. But you know, hey, we're here and we're doing physics and it's almost the weekend, so something to ponder about over the weekend while you're all enjoying socially distanced fun, right? That's what you're gonna do this weekend, right? Because I think if there's one thing I've learned from watching the news lately. Okay, do you know what I've learned from watching the news? Germs are real. Wear masks. You can draw your own conclusions from it. Yeah, the pandemic's been on the news a lot. There's germs are real. That's what I've learned. Okay. So if we call this C, which is equal to V times T, okay, now let's go over here. All right, so let's write this another way. Let's say C divided by V is going to equal some time quantity here. What could that be? I wonder. Well, let's invert this. All right, let's say let's take our equation over here. It looks like C over V is equal to T, so then this would equal 1/T. Wow, I think we derived something really awesome. I don't know. We built some awesome machines today. We derived an awesome equation. What could be awesomer? Not a lot. All right, what is this quantity T? What is that time right there? There's a name for it. But what is it physically? Okay? If we have V divided by C, so that's our, we go back over here to Newton's equation, okay? If we take x divided by v, that's going to equal, yes, it's, well, yeah, it's period. It's period. All right, spoiler alert. Somebody ruined it. It's period. Yes, you're right. That's the time it would take our particle No, it's okay. I'm glad you said it. I'm glad you know what period is. That's great. Hopefully you remember from high school physics. Okay. Well, that's the time it would take for our particle to go around a loop. So that's the period of one rotation. So this is actually something called period, which is one over t, which is the period. Okay. And so what we derived really is 1 over t equals our frequency. Okay. So frequency is equal to 1 over period. Okay. And up here, okay, let's go back up to this part here. Okay, because this is what we're doing. Okay. So now if we take our circumference here on the bottom and we separate that into 2 pi r, then we multiply the top and the bottom here. So this would be 2 pi, and we'll multiply here by 2 pi. Our 2 pi's will cancel. We'll get 2 pi times f. This is something called angular frequency. Angular frequency. Yes, it's the weekend. All right. I don't have to spell frequency. Oh, man. Okay. All right, so that's our angular frequency. Oh wait, no, I know how to spell frequency. There it is. Okay. All right, so our angular frequency. You know what? It's the weekend. I don't care. Here's our angular frequency. Now we're gonna say that omega is equal to v over r. Okay, let's go here. Omega is equal to v over r. This is important. Omega is equal to v over r. But we know from up here, let's go back up here, this is v over r, okay? So now we can set this equal to q times b over m, okay? So what we're getting at here, and we'll set this, we'll say this is 2 pi times f times qb over m. So then the frequency of our cyclotron, okay, so we'll say, we go up here. Oh, I better start a new page. It's starting to get out of control. Oh my goodness. It's just writing everywhere on the page. It's getting a little crazy. All right, so F is equal to Q times B over 2 pi m. This is the resonance frequency of a cyclotron. And if Cyclotron were a transformer, he'd probably be a Decepticon. Okay, enough jokes. All right, let's look at a problem from the homework. I think it's a good one because this is okay. Let's look at this problem because now we are set up to do problems about cyclotrons. Okay, we know how to do to get the resonance frequency of a cyclotron. Let's look at one of your homework problems. All right, here we go. We can do this, guys. A certain cyclotron, in a certain cyclotron, a proton moves in a circle with a radius 0.51 meters. The magnitude of the magnetic field is 0.92 Tesla. Haha. Look what we just did in class. I helped you with your homework. You thought I was just rambling like a crazy man, but no. We're actually helping you with your homework. Oh, and I'm showing you the answers. Oh my gosh, what the? Well, you probably have different numbers, so it doesn't matter. Yeah, okay, whatever. I don't care. But if this were on a test, now you need to know, what is this witchcraft? I don't know. Okay. So we have a cyclotron. We know we're given the radius of the cyclotron. Okay. And What else are we given? Yeah, we got the right answer. Yeah, we did. Okay, then what is the oscillator frequency? And what is the kinetic energy of the proton? All right, well, we've got the first parts, okay? We can find here, we know what our resonance frequency is of the cyclotron, okay? For this problem, it's a proton, so we know what the mass of Q, we know what the charge of Q is. We know what the proton's mass is, and it gives us the magnetic field, okay? So we can do part A in this one. How do we do part B? Let's take a look at part B. What is part B asking us for? Let me share my screen again. Okay, so part B says, what is the kinetic energy of the proton? All right. Well, if we go back to what we had before, or what we did last time, now we should be able to get our kinetic energy. And we did this last time. Okay, so if you recall, let's go back to our, let's back up a little bit. We know that the force due to the magnetic field is equal to Q times V times B. And we know that this is equal to its centripetal acceleration, which is mv squared times r. Okay, we did this problem last time in class because now we know what its radius is. We can solve for its velocity, and so you can get the kinetic energy. Okay, so this is how you do it. We derived the expression, we derived the expression for the resonance frequency of a cyclotron, and now we can get its kinetic energy if we know the velocity. So, all right, that's it for today, guys. I feel like we covered a lot of ground in class today. We made some awesome devices, and it was all for a reason. We made a cyclotron in class. We also made a way to transmit power wirelessly. Okay, so that's a pretty cool device. All right, so have a great weekend, and I will see you guys on Monday. I hope you all do something safe and socially distant this weekend. Because remember, you don't want to go live at home with your parents. Only you can keep you from living at home. So wear a mask. Oh my gosh. Okay, guys. Have a good weekend. I'll see you guys later. And I'll stay around if you have a couple questions. But I think my son, I need to go. My wife has a meeting, so I actually need to go. But I'll stay around for about 2 or 3 minutes, and then I need to go see what my son is up to. All right, guys, have a good weekend. Bye. Bye. Have a good weekend. See you later. Bye.
Thank you. Like and subscribe down below.